Welcome again to the HFWorks video tutorial series. Today we'll show you how to perform a thermal simulation for a dual band 5G bandpass filter right inside SolidWorks. As usual, right click on the project name and add a study as parameter. Click on frequency sweep, choose fast sweep, starting frequency 27 gig, ending frequency 29, number of points 100. Click on the meshing tab, take the default adaptive mesh, coupling analysis, right click thermal coupling, click OK. A new study is added to the feature manager tree. Now we're going to start applying material. So the housing is just copper, right? So favorite material is copper. Part 1 is the actual cavity filter, which is air. My favorite is air. Now part 2 has 4 bodies. 2 bodies are the inner or central conductor of the coaxial cables. Right click, apply material, or you can use again copper, and then the dielectric itself. Right click, apply material, the material library opens, material browser, so you click cables, scroll down Teflon, add. So now we apply the material. So it's so simple. Boundary condition, actually there are only 2 boundary conditions to apply here. It's port 1, that's the coaxial cable, port 1, and port 2. Click. That's all you need to do. As far as meshing, you don't need to mesh because you selected adaptive meshing. Let's go straight. And by the way, because it's coupled to thermal, see there's the thermometer symbols right here to tell you that this study is coupled to thermal. So once you click run, it will it will run the electrical part and thermal part. Let's look at the results straight now. This was with the same setting solved earlier. So you click on to look, you can look at the results. You can click electric field. Okay, you can look at the results table. At each frequency you have all the S matrix and port results. You can plot your S11, S12. As you can see, it's a dual pass filter with 2 pass bands. So this is the first one, this is the second one. Okay. Now, the nice thing about HFWorks, the thermal solver is completely integrated inside the study. So there is no such thing as electrical solver, high frequency solver, and thermal solver. They all want the same feature manager tree. So the thermal load, due to the dielectric and conductor losses, are automatically transferred to the thermal solver. Okay. So once its electrical part is done, you can create a new thermal case. You can do steady state or transient. Let's do steady state. And you decide how much power you apply at each port. Say on this one I can apply 50 watts, and maybe port 2 I can apply 100 watts. Okay. So the nice thing, I can run as many thermal cases as I want without rerunning the electrical part. So let's look at some results that I solved earlier. So this one is a steady state with 5 watts. You can look at the temperature. That's your temperature. You can do, if you wish, a section clipping. You can see inside. Okay. You can plot the section only. Click OK, and then you can actually animate versus cut section cuts. So it will automatically generate many cuts for you. Okay? And this, it allows you to look really inside your structure. Okay, done. If you can also to do a 2D plot. Suppose you want to see the temperature between 2 points, say, or many points, this point, and say, I don't know whether at this point. Click OK, and that's your temperature as a function of distance between point 1 and point 2. Okay. All right. Let's look now at transient thermal results with the 50 watts, and the simulation time is 1 minute. So if you see the property here, thermal, okay. This is 50 watts at port 1. That's all. Okay. And then once you run, you can look at your results here, and I can, because this is a transient thermal, I can animate as a function of time. As you can see, the shape is the same, except the values keep changing. Okay, that's the transient solution. Again, you can do a section clipping. Okay, and you can again animate versus cuts or versus time. Let's do versus cuts again. And this is, by the way, it's time step number 3. Okay, so you can run as many thermal case as you wish to. You can change every time. You can change the input power at each port without again rerunning the electrical part, because the thermal load are automatically applied. Okay. Last but not least, you can at the end generate a report. You can customize it. Okay, you can put my company logo, author, company, date, or the HTML file, and then I'm going to click OK. That is going to generate a report, a full HTML report that has all the information, the input, the pre-processing, the post-processing, and the results. So if I want to look at the magnetic field, electric field, boundary condition, say if I want to look at the port field, so you don't need to write down anything. It's the report is HTML. You can produce a PDF file, or you can share it with coworker because it's just an HTML file. So that's basically how easy it is to study the thermal effects on a 5G dual band bandpass filter. I can, if I want to say change something quickly, I don't need to recreate the study. I can simply make a copy. Again, maybe call it study 3 and say OK. Okay. Now it's copying my study. Okay, my study is copied now. I can change, say I want to change the material. Okay, I can change the material, say from Teflon, I can change something else. Say I right click, okay, edit, if you want to edit, yeah, I can actually edit the material, okay, or apply different material and run again if I wish, or I can generate many different studies, and before I go home in the evening, run out studies. That's it, that's all. Thank you for your time. Bye.